the rest of this week and next week for our unit is chapter 4. A lot of times I like to start a chapter with a reading guide, but for most of the other parts, there's not going to be a reading guide, but if you want to kind of keep up with the class, it all comes from chapter 4. Yes?
This is unrelated, but you said that was our stomach acid, but it's hazardous, so how is it?
Well, so it's in your stomach, I think it's around 0.1 molar, so it's still, it's only half as concentrated as my bottle was, so it still is it can be damaging, but your stomach is lined with mucous membranes, and so all that mucus protects the cells themselves. But you need a pretty strong acid in your stomach to break up the food and kill any germs as well that might have been in the food.
So what if you throw it up?
Exactly, and you do throw it up, right? It kind of burns. Have you ever noticed it? It burns the back of your throat, and then that's one of the issues with people who have, suffer from eating disorders like bulimia. Their teeth eventually start to degrade a little bit because that acid kind of eats away at their teeth and even the back of your throat. If you're like, does anyone else have acid reflux? I do. I have acid reflux. I take a medicine for it every day. So that gets to the point where it damages your esophagus if you have some of that acid that's always bubbling up. So your stomach's supposed to be pretty well sealed off to keep that acid in there, where the mucous membranes can be pretty protective. So that's how you're able to have a strong acid in your stomach without it doing damage to anything except the food that you want it to kind of break down as you eat it.
So everything's lined, but say you licked up your throat. Would that damage you because it's the acid?
Over time it would, and it does, because that if you have acid reflux like me, it actually hurts and damages your esophagus if you don't take your medicine. So yeah, and it's not even that. You could put your finger in it and take it out and wash it off, and unless you have really dry or sensitive skin, you'll never notice that you did it. But if you left your finger in it for a few hours every day, over time, it's going to eat away at your skin.
Just bones.
At that concentration, probably not, I guess, but if it were 6 molar eventually, yeah, it would. So it's the reduced concentration and the fact that your stomach is lined with that mucous membrane, and the mucus protects your cells from the damage. Yeah. Yeah, over time, it could start to break up food. When we used to have to do science projects, one group did an artificial stomach or something, and they did try to put food in and watch it kind of slowly break down over time. You've got a lot of enzymes in your stomach too that help out with that, but yeah, the acid helps to break down the food.
Yeah, I have some. Let's put a cheddar out.
See what happens over the next week or so.
Yeah.
That would be a neat experiment that we could try. It'd be really gross, but we could throw it in there at the end of the class and see what happens over a week.
I think that would be so
Okay, yeah, that's cool. Go ahead. All right, let's get into this stuff on aqueous reactions. So first of all, aqueous solutions, we read about that. That's just any solution that's water-based. And now we're going to get into this, practice another dissociation equation. Unfortunately, I picked a sulfate again, so we've seen it before, but it's a good example to look at. So we're going to write the reaction equation for the dissociation of Li2SO4. So dissociating means to unassociate or to break apart from each other. If they associated, they would have gotten together, but now they're dissociating. So we're going to start by rewriting the compound, which is just Li2SO4. All right, it's a solid. Ionic compounds are going to be solids on the left-hand side. And we have our reaction arrow. Then, once again, subscripts are going to become coefficients unless that subscript is part of the polyatomic identity, because polyatomics individually stay together. So this 2 right here is going to become a big 2 on the other side, coefficient. Then we write the element name there, Li, element symbol. We're going to put its charge. Right? You may just look at the periodic table perhaps, or you may figure it out from the fact that it takes 2 of them bonded to sulfate, which we know is -2. Each lithium is +1 in charge. And then we're going to put AQ. AQ means this is now, each of them are now surrounded by water molecules. Plus, then we'll say SO4. There's only one of the SO4s because there's no like parentheses around the SO4 in the original formula there. We'll put its charge. And then we'll also put AQ there. All right, that's the dissociation reaction that we're looking for. Underneath it, I'm just going to draw a particle diagram just to kind of think about what was going on here. So at first, the individual Li plus, another Li plus, and then a sulfate. I'll draw a sulfate like this, which is SO4. See, the sulfur and the oxygens are covalently bonded to one another, so the water molecules aren't able to break the sulfur away from the oxygen. But then, when it dissolves, the water molecules are going to get in there, and you're going to have two separate lithium ions, and then the sulfate's floating around separate from those guys as well. And what those water molecules like to do, so when we put AQ after these things, that reminds us that the water molecules, they came around and they surrounded each one, and they're the things that pulled apart the lithium sulfate. The oxygens are negative, so they like to get up close and personal with the lithiums. Remember, water has that bent shape. And then the hydrogen end of water is positive, so it likes to get up to the negative sulfate ion. So the thing on top is the actual reaction. That's kind of the answer that we're looking for here. That's the dissociation equation. But just what it means in terms of the particle diagram, that's what's going on when we dissolve an ionic compound like lithium sulfate. So individual polyatomic ions like sulfate, those elements are still stuck together, the sulfurs and the oxygens. If you ever have multiple polyatomics, like if it were SO4 parentheses 3, then you could have 3 separate sulfates floating around, but the S and the O within each sulfate unit, those stay together. So don't break up an individual polyatomic ion from itself. Does anybody need more time here? Because when I hit next, it clears. All right. This was the question on your assignment there. We ended up going with choice C, so lithium sulfate dissolving in water. We went with choice C, and again, that's because we knew there's a lithium sulfate once it's dissolved. There's another 2-to-1 ratio of lithiums to sulfates, and there's another one. So this was 3 formula units of lithium sulfate dissolving. Why is A not a good choice? Yeah. They stay together. A didn't ionize. A didn't break up. All right, so that's not going to happen. And then, why do you think B is a bad choice? Yeah, the ratio is wrong. It's a 1-to-1 ratio. Actually, no, it's a switched ratio. It's got 2 negative 2s for every 1 positive 1s. Good. All right, now, I'm going to write these on the board so it's a little bit easier to see those strong bases. These are your strong acids and strong bases. On Tuesday of next week, I'm going to give you basically a blank piece of paper, and I'm going to say, list and name the 7 strong acids and the 8 strong bases. And the acids, you got to work to memorize them. The bases, it turns out, are actually not too bad to memorize. I'll list them on the board as well. The strong acids are listed pretty well up here if you want to go ahead and list your strong acids. For the strong bases, I'm going to list them a little bit differently. with the strong acids, if you kind of group them together, it's not quite as big of a task to memorize them. The first three, HCl, HBr, and HI, if you look on the periodic table, element 17, element 35, and element 53, all right, those middle halogens there, they're all kind of clumped together. So you just put an H in front of those three elements, and you've got your hydrochloric, hydrobromic, and hydroiodic. Then the next two, all right, we learned chlorate, the polyatomic ion. So hydrogen and chlorate, and then hydrogen, this one's called perchlorate. So HClO3, HClO4, those are next, those are kind of clump those together to learn those. And then nitric and sulfuric, they're just kind of oddballs there. That's hydrogen nitrate and hydrogen sulfate would be another way to state those names. Those are your 7 strong acids. Those are the only acids that dissociate 100% when dissolved in water. If its name ends in acid and it's not one of those 7, then they might dissociate a little bit, but not 100% dissociation. All right, now the bases are even easier to learn. You just use your periodic table. So underneath hydrogen on the base side, 1, 2, 3, 4, 5. We go from lithium, sodium. So these are our group 1 hydroxides. You just look at your periodic table, which is always on the wall over there, and you stick OH next to them. So it's lithium hydroxide, sodium hydroxide's the most common one that we talk about, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. So those group 1 metals, alkali metals, notice hydrogen's not included because that would just be HOH, which is water. So it's those group 1 metals plus OH. And then I think francium, I don't think is like stable. I guess it would be one, but I don't think francium lasts long enough to bond with hydroxide. Or if it does, we just never think of it as a strong base. So don't worry about francium hydroxide. Those are the first ones. Then you go to the lower part of group 2. All right, so we're going to go with our calcium, our barium, and our strontium. Strontium's first. Calcium, strontium, and barium. These have a +2 charge, so each one of those needs 2 hydroxides. So that's why it's CaOH2, SrOH2. And because remember, hydroxide has a -1 charge. Those are group 2 metals, so they end up with a +2 charge. So those are ionic compounds on the right-hand side. So they definitely dissolve in water. That's what makes them strong bases. They dissolve in water, and they conduct electricity because they're ionic for the strong bases. And for the names, again, you just always name them calcium hydroxide, strontium hydroxide, barium hydroxide, cesium hydroxide. So they're just named like any hydroxide ionic compound would be. The thing is that if you had beryllium hydroxide or magnesium hydroxide, the top 2 in that group 2, they don't like to dissolve. So the reason they're not strong bases is because you could stir and stir and stir those in water and they don't dissolve very well. Even calcium hydroxide takes a whole lot of stirring to get it to dissolve, but eventually it will. So on Tuesday, again, I'm going to give you a blank piece of paper and I'm going to ask you to list and name the 7 strong acids. So you can list something just like this. They can go in any order as long as you've got all 7 there, because it won't be matching, it'll be blank. And then you just have to give me the formulas for the strong bases because their name is just the metal hydroxide. So start learning those. Maybe learn first 3 strong acids today, the next 2 tomorrow, nitric and sulfuric the next day, and then on Monday you can make sure you know all of your strong bases, and then you'll be ready for Tuesday's quiz. Make a good score on it. All right, moving on from that, let's get back into, I guess I went a little out of order here, but we've got some strong acids on this. So now let's get into that example, lithium sulfate that we just did. And I've got this printed actually for you here. So if you'd rather do this on this handout, I'm going to pass this out. This looks like homework because I just selected some questions from the book, but this is actually just some notes questions that we're going to go through together. got 4 ionic compounds here. And that is one of them is a strong acid. What's covalent? Which one of these is our covalent strong acid? A, B, C, or D? Yeah, good. C is that strong acid. But it's going to do the same pattern that the ionic compounds do when it breaks up in solution. We've also got some different polyatomics to look at here, so we'll see something other than sulfate. All right, let's look at the first one. It's probably the simplest on here because it's just a binary ionic compound. There's no polyatomics with it. So the very first thing I write down is basically what's given to me right there, MgI2. It's an ionic compound, so I'll put solid after it. All right, then I'll do an arrow. Then I want to break it up into its ions, and subscripts will become coefficients unless it's part of a polyatomic ion. I know there's not a polyatomic ion here because there's just 2 elements. So if there's just 2 elements, you don't have a polyatomic. All right, so I'm going to have Mg. Then I'll put its charge. What's the charge of magnesium as an ion? +2, good. I'll say 2 plus, but I'm fine. If you put +2, that's good too. And then what am I going to put after that to show it's dissolved in water? AQ, good job. Plus. Now what am I going to do with the 2 after the I? Yeah, it comes before the I here. And, you know, sometimes people worry about their diatomics, and they're like, but isn't iodine a diatomic? It is, but that doesn't affect ions, all right? That only affects pure, solid iodine, the pure element, not as an ion. This ion is now floating around in solution, so don't worry about your diatomics when you're doing dissociation equations. All right, let's look at letter B. Letter B has a polyatomic, but it's also got parentheses around that polyatomic, so I want to make sure you know the difference between the 3 that's part of nitrate and then the 2, actually that's another, and the other 3 that comes after the parentheses here. So again, let's write down the compound. Ionic compounds are solids, so we know to put that. All right, what's going to come? You can help me out with this one. It's the wrong class. Well, I lost my cards here. So what's going to come first for this one? Pavitra, what do you think is going to be our first species on the right-hand side of the arrow here? Aluminum. So yeah, we're going to put Al, and we'll put its charge. So Maddie, what's the charge of aluminum? 4. Close. 3 plus, you got it. Why did aluminum not need any kind of a coefficient here? Doesn't have a subscript in the formula. Good. There's just one aluminum in aluminum nitrate. All right, now here comes a tough question here. So do your best. He's not here. Claire, what do you think we're going to put next here? Good. You're exactly right. So that 3 is important because here, this outside 3 is not part of nitrate's identity. So this 3 is going to become your coefficient over here because there are 3 separate nitrates. Good job, Claire. And then we'll put the whole formula in nitrate. And Davis, what's the charge of nitrate? Negative, yeah. And then I'll put AQ after it. Show that. Great job. So do you see the difference between the 2 3s? The 3 outside the parentheses for a polyatomic does become a coefficient because there are 3 separate nitrates. The 3 inside the parentheses is part of nitrate's identity, so nitrate sticks together. All right, let's try letter C here. This is our perchloric acid, strong acid, so it gets treated. I'll put parentheses around it just so you can kind of see what's going on here. I'm not sure of the state of HClO4 as pure. No, HCl is a gas, but I don't know about this one, so I'm just going to not I'm not going to put a state of matter symbol on this one. But now we can see perchlorate is just like any other polyatomic ion. All right, so we can see it like that. What do you think is going to be our first product on this side? Mackenzie, what would you guess? You got it. We'll put its charge, H+. We'll put AQ, that is surrounded by water molecules. And again, if you ever see the word proton, okay, H+, aqueous, we're talking about, it is just a proton that's floating around. It finds a water molecule to attach to, and that's what the AQ means. All right, and then what else are we going to have here? Alice, what would you guess would be our next product? Good. So that's a polyatomic that I didn't make you memorize, so it's a little new, but it's perchlorate. We call it ClO4. It's just like chlorate would have been. And then we'll put AQ. All right, we got one more on there, which is, let's name this one. What was the name of this one in the first place? I see a sodium, and then I see chaku, right? Adam, what is chaku? Yeah, good job. That's acetate there. So we've got sodium acetate, and we're going to break it up. Sydney, what's my first product going to be here? Good job. Na+, AQ. And Kira, what's my next product going to be? Yeah, good job. Keep the acetate together. And it's a 1- charge. I know that because it's bonded to a single sodium, or maybe you remembered the charge from before. Anybody need more time here? Okay. Get this to go to the next slide. There we go. All right. For the electrolytes, this is the kind of demo I did, but they're using just a regular light bulb here. First of all, if you have a non-electrolyte, you have no ions. So a non-electrolyte solution doesn't contain any ions, so it didn't light up the light bulb. That's what our sugar did, okay? Sugar did that on this side. Next, we're going to have weak electrolytes, and on the next slide, I've got kind of a chart summarizing this stuff. Weak electrolytes, there's a few ions in the solution, but there's also a lot of molecules that are still stuck together. And even the percentage of this is kind of exaggerated, so you can see some charge. Really, it would probably be like 99 molecules for every 1 charge, but as long as we see this half molecules or half charge or something about that amount, they're trying to emphasize the fact that there are some ions going on, but there are some neutral molecules. That would light up the light bulb just a little bit. And vinegar is it's acetic acid. It's an acid that's not one of those over there, so I know it must be a weak acid. Things like vinegar do that. And then finally, many ions, that's going to be our ionic compounds, and our strong acids are going to do on the right side. They're going to be strong electrolytes. So this is a chart. If you wanted to summarize it, I made this chart here to kind of summarize our strong electrolytes, our weak electrolytes, and our non-electrolytes. Non on the first slide, though. So I'll just make that line a little darker there. Here we can see this chart. All right, non-electrolytes include almost all covalent compounds unless it's one of those strong or weak acids. Covalent compounds, they do not like to dissociate. Our weak electrolytes include a few covalent compounds like the weak acids and weak bases. And then the strong electrolytes are ionic compounds that dissolve. Obviously, if it doesn't dissolve, it can't be an electrolyte. So we'll look at our solubility rules a little bit next week to go over that idea. But soluble ionic compounds, and then also the strong acids and strong bases. The strong bases actually are ionic compounds, so that's why they conduct electricity. The next thing we'll do is we'll look ahead. We'll do this question on the upper right. So there's a made-up molecule called HA in each case here. Made-up compound called HA. Which one would you guess is more likely to be the weak electrolyte? So we're going to do that chart now. HA is kind of the generic term for any old acid. You'll notice the pattern acids typically start with H and then something else. So if you want to represent something as an acid but you don't know what acid it is, you can call it HA, where the A kind of indicates acid, because there is no element A. I'll come back to that one in a second. All right, so which one of these is most likely the weak electrolyte? MK, what would you guess? Yeah, the second one doesn't have as many charges there, so we're going to go with this one. In it, there's still a lot of molecules that are still stuck together as HA that did not dissociate. So all those failed to dissociate, so they're not helping out to conduct electricity. The one on the left-hand side, that's a strong electrolyte. That must have been a strong acid, because every single species in there is now a charged ion. All right, last thing I want to do is at the bottom of your sheet, last thing for today, so we won't get into the molarity stuff until Monday, but we know a little bit about molarity from the lab so far. But it says HCl is a strong acid. What solute species are present in a solution of HCl? Oh, well, we saw that earlier. All right. When HCl breaks up, what are the ions it breaks up into? Joseph? You got it. So we're going to have H plus and Cl, just identifying them. The ionization equation, this is a strong acid. Strong acids, when they dissociate, they use that one-way arrow. This is what, there was that one question about the absence of a left arrow for HCl. So it broke up into H plus and Cl minus. All right, we haven't talked too much about weak acids. But HF, it is kind of strange that HCl, HBr, and HI were all strong acids, and then HF got left out. That's because the H and the F, they have a really tight, strong